there are two different ways that we can draw a dissolvent. And usually water will be the solvent. That's far and away the most common. It's just a matter, are we using an ionic compound or are we using a covalent compound? So on the drawing dissolving how-to sheet, number one, we're going to draw, right above it says, follow the steps below to draw the dissolving of a solute in a solvent. Let's use the example of water and lithium fluoride. For my number one on the sheet, I just want to remind you of what water and lithium fluoride would look like. Remember, we draw water bent, not linear. This gives us a partial negative end on the oxygen end, and the hydrogen ends are the partial positive. Two reasons why the oxygen is the partial negative. Oxygen is more electronegative than hydrogen, so it's an unequal sharing of electrons between the hydrogen and the oxygen. But also those lone pairs of electrons on that central atom creates a region of high electron density. Lithium fluoride is an ionic compound. It would look like that. In step 2, it says redraw the Lewis dot structure so that the opposite charges are next to each other with the polar covalent molecules and more electronegative atom, partial negative atom, so on and so forth. So one of the things to remember when dissolving ionic compound, and maybe I'll just skip to number 3 to do that as well, is that the ions separate from each other. To dissolve an ionic compound, the Li plus and the F minus separate from one another. So again, if I just skip down to number 3, what our final answer is, not only do they separate, but water now has to align itself where opposite charges attract. That means the hydrogen end of water would be attracted to the fluoride ion. The oxygen end of water would be attracted to the lithium ion. Last thing to note is that dissolving requires multiple water molecules to surround. I usually show a minimum of 3 water molecules around each ion to demonstrate that. Notice how one water molecule isn't used for both ions. I know some students try to cheat that in a little bit, where if I just put one big water in between the lithium and the fluoride, I can count for both. That's not how it works. Again, water can't do double duty in that sense, which is why when you go back to the lab that we just turned in, the 8% saltwater solution was not very good at carrying things up the paper, because the water already was carrying 8% of salt up the paper with it. So some of its hands were already full, and now it also has to attract to a dye and carry that up. It wasn't very easy. The 0.5% was much better at grabbing hold of the dyes and pulling it up, because it had less things that it was carrying along the way. Now this is one way that we can draw dissolving with Lewis dot structures. I want to show you, and it's a little hard to see because I had to expand it out. Another common way that the AP will ask you to draw dissolving is, instead of doing Lewis dot, to do it more in a, here's what a molecule of water looks like on the left-hand side. Here's a whole bunch of crystals of lithium chloride on the right-hand side. So what you'd have to recognize is, first off, in the lithium chloride, there's small lithium ions and there's large chloride ions. So they would want you to draw a small circle and then a bigger kind of shaded in circle. This is water right over here. where it kind of looks like Mickey Mouse with the two ears and then the big circle in the middle, almost like what you had in freshman bio when you had to make water molecules. So you'd have to recognize that if this is water right here, this is the hydrogen end, this is the oxygen end. So if I were to draw that, remembering that this open small circle is lithium, which is a positive ion, the oxygen then would be attracted to the lithium. The hydrogen end would be attracted to the chloride. So again, there's two different ways that this can be drawn out. You can do it in Lewis dot, which is what we typically show in class. Now the issues with that is this does look a little mucky in here. Now some people would put brackets around their ions to try to help out with clearing up some of the muddiness of this. But I've also seen them ask questions, because this I specifically copied from an old AP free response that they do have online. So those are both ionic examples. What I want to end with, which isn't actually on your how-to dissolving sheet, so maybe we want to do it on the back side, is what if we have a polar covalent solvent, like ammonia, NH3. Ammonia is a very common weak base. So in second semester, when we go over acid-base chemistry, ammonia comes up very often. If we dissolve that in water, if it's polar covalent, which you would recognize by the fact that there are no cation, anion, metal, non-metal parts, it's all non-metals, the ends will not break apart, the H's will not break apart from the end. It all stays together when it's a covalent bond. But just like before, it has a partial negative end. And then it has a partial positive end. So what I would do is have my water surround that, so opposite partial charges attract one another. This is actually creating hydrogen bonds. NH has a big enough difference in electronegativity that can create hydrogen bonds. Again, it doesn't necessarily matter how many waters you put around it. I like drawing these out in Lewis dot because, to me, these AP free response questions take little parts of different units and put them together. And I could easily see them asking stuff about the shape. I mean, NH3 has its own shape that you should be aware of. Not only that, but once we get into second semester, they can start talking about the acid-base properties of these things as well. So there's a lot of things that they can mix in to make this work. Again, WebAssign being computer-based, we're not going to have any drawing dissolving on there. But at the same time, I wanted to remind you of this, but I don't know if we really need much practice with it because this is something we covered in Chem 1. I just wanted to bring it over with you. Do you guys have any questions on this at all? All right, so then we're going to go straight into notes about concentration. Now, the good news about concentration is the old AP standards would have us not only having to know about the 4 different ways to calculate concentration, but also you'd have to be able to mathematically convert from one to another, which isn't easy. The new standards are less about doing that mathematical process, but more just being aware of these different units of concentration. The first one we should already be aware of is molarity. And molarity is your moles of solute divided by liters of solution. That's how we'd abbreviate that equation. You learn it in Chem 1, you learn it in AP Chem, you have to do solution stoichiometry with it in AP, you had to know spectrophotometers, how that's related to absorbance. This is, by and large, the most common unit of concentration. However, it's not the only unit of concentration. That's what we have to go over today. So I'm not really going to go over any practice problem with this because you guys know how to do this. Usually you're given grams, you have to convert to moles. Maybe you have to solve for molarity instead. Molality is the second unit of concentration. Yeah. Let's make it basically the same word, but just switch one letter to throw you off a little bit. Let's use a lowercase m, which should be for meters, but we're going to use that for molality anyways, because again, we're just trying to make life difficult for you. Molality is moles of solute per mass of solvent, and that mass is in kilograms. Molality would be moles over kilograms. Yes. Hey, remember that 1 gram of water is 1 milliliter of water? Well, metric-wise, that means 1 kilogram of water would be 1 liter of water. So, why? Why would you do this to us? Molarity is such a nice, neat thing, and now you introduce molality to us. First reason why we have a unit of concentration called molality is because molality is independent of temperature. Both molarity and molality have moles of solute in the numerator. The only difference between them is the denominator. In molarity, it's liters of solution. In molality, it's kilograms of solvent. Liter is a unit of volume. Kilogram is a unit of mass. One of those two is dependent upon temperature. The mass of a substance does not change regardless of what temperature it is. The volume, however, can change. When you heat things up, they spread out usually. When you cool them down, they usually get more compact. So molality is used typically in instances of extreme temperature, really cold or really hot, because molarity can't stay constant based upon the temperature. I mean, even the periodic table, when it gives the values of things, it usually says this is at 298 Kelvin. The reason why they have to report a temperature is they know volume changes based upon temperature, and every number dealing with density and things like that in the periodic table would change then if it was at a different temperature. Molality is trying to adjust to that. Second reason, molality is only based upon how much solvent is in that solution. So how much water did you add? Molarity is the volume that's combining the solute and the solvent. Now, typically when you make a solution, what you're supposed to do is maybe put a little solvent in the bottom of a flask. So remember, we actually used volumetric flask when we did our spectrophotometry earlier in the year. Maybe you have a little solvent in the bottom, then you add the solute, and then you add until you get to your line, and then you have that solution. Mix it up, and hopefully it stays in that line. If not, add a little bit more. Molality, you don't have to worry about, is this the perfect amount? Because you just have to measure out the mass of usually your water. Now, that being said, we primarily will stick with molarity as our unit of concentration. However, the topic that we covered next class called colligative properties, which kind of wraps up solutions, Molality is what they usually use in describing freezing point depression and boiling point elevation. So that's why I want you to at least be aware of it. The odds of me on a test asking you to solve for the molality of substance, I think is pretty darn low. Molarity is usually the main unit of concentration. Percent by mass. This is what we did in the lab. This is what we used in the lab last time. Mass of solute over mass of solution. Multiply by 100 to express it as a percent. Percent by mass, I would say, is the primary unit of concentration used throughout the world. Because most people aren't chemistry students and know that molarity is the best thing to use. You go to Piggly Wiggly and you walk down the aisles, you will see things labeled with percent by mass. Rubbing alcohol, 70% by mass is typically what that's sold in. Hydrogen peroxide, 3% by mass. Usually everything is given in a percent instead, because to have the general public know about molarity would be too much for them. But percentage of how much of this in the total, I get that. Oh, it's a high percent? That must mean there's a lot of stuff in it. It's a low percent? No, it's a low amount of stuff in it. That's why there's no mole conversions within it. So the example I give in the bottom here, and actually the last lab that we do this semester. So if the test that you guys have is on Monday the 7th, Wednesday you have a lab. And in that lab, we're going to take household hydrogen peroxide, which is labeled as 3%. And we're going to find out what the molarity of it is by doing a titration with it. But what that 3% means is there's 3 grams of hydrogen peroxide for every 97 grams of water. If it was a 100 gram sample. It could be 6 grams for every, do the math, for a 200 gram sample. Debbie? Yeah. So the total mass of the solution is the mass of the solvent and the solute added together. So that's where that would come from. So when I made your saltwater solutions of 0.5, 2%, and 8%, I had to know how much mass of water I had and how much mass of salt that I had to put the two together to make it in those certain percentages. So just another way that it is expressed. Again, not a very common way for you to have to solve for it in this class, but sometimes they are given in those values. And actually, all the acids that I purchased, not only do they give me a molarity, but they also give me a percent by mass on the label. Now the last one, we should already be aware of from when we did gases and partial pressure. So the last one isn't actually unusual. It's mole fraction. Moles of the part divided by moles of everything. Again, our text, or I believe the equation sheet gives you X, like XA, so the mole fraction of A is the moles of A divided by the total moles. And I believe that equation is given to you on your equation sheet. We've already used that. Oh, darn. We have already used this equation with partial pressure this year. Next class, one of the colligative properties that we're going to discuss is talking about how a solution has a different vapor pressure than a pure substance does. So mole fraction is often used in that regard as well. But I would say mole fraction is one that you do need to be aware of, because that's what we use for partial pressure of gases.